Alright gang, here we go. This is for Chem 2 Unit 9, talking about reaction rates. Okay, I'm going to talk about three different types of reaction rates in this video. Average rate, instantaneous rate, and initial rate. Okay, so rate, remember when we talk about reaction rate, essentially we're talking about how fast does our reaction take place. And if you have any background in physics or anything like that, you can really think about this in terms of, almost like velocity, right? It's the change in something over the change in time. In this case, because we're talking about chemicals, we're going to do it as the change in concentration. Okay, the change in concentration over a specific time period. All right, so remember this delta sign means change in. Okay, these brackets, square brackets, always mean molar concentration, right? So whenever you see these, it's always in molarity. Primarily, when we talk about reaction rate, we're talking about it as molarity, or change in molarity per change in time, or change in molar concentration per change in time. All right, but really we could do it in anything per time. We could do it in grams per time. We could do it in molality per time. We could do it in percent mass per time. We could do it in atoms per time. It doesn't really matter. Primarily we're going to do it in molarity per time because it makes it easy to measure and work with, because we can just use our molarities that we already know for our reactants. All right, and then our time could be in seconds. That's the SI unit, but it could also be minutes or hours or days, just kind of depending on whatever the reaction is, however long it takes. All right, we're going to talk about these three different types: average rate, instantaneous rate, and initial rate. All right, so if we have this reaction, we've got this compound here reacting with water to form the same thing, but it's replacing the chlorine with this alcohol group here, and then hydrochloric acid. Okay, and so when we measure the rate of reaction of this thing, we're really just going to measure the change in concentration of something that's in it. Specifically, we probably wouldn't choose water because we can't get concentration of water, so that one's out. But really, we could pick any reactant or any product. Okay, the reactants are going to be getting used up, and then the products will be getting formed. Okay, so if we were going to write the rate of it in terms of this reactant here, this is what it would look like. It would be the change in this compound over the change in time. Now notice that we put this negative sign in front of it. That negative sign is there is because it's a reactant and it will be going away. So this change in this reaction concentration, or this reactant concentration, should be negative. It'll be going down over time. Okay, so our rate will be the change in this concentration, lowering over time. Okay, and we can kind of see this going on. So here's the reaction, and it's going on in seconds. We're going up by 50 seconds here, and our initial concentration was 0.1 molar. At 50 seconds, we measured it as 0.0905 molar, and then 0.0820 molar, etc., down until there was nothing left at 10,000 seconds. Okay, and so at between each one, they calculated the average rate. Well, we know, we just established that the rate was equal to the negative concentration of this guy, C4H9Cl, over the change in time. Okay, so essentially what they're doing, remember, whenever we see the change in, this is always going to be the final, okay, final minus initial. Right, that's the standard way of doing this. So in order to calculate this initial rate, they would take their final concentration, so that would be that, so 0.0905 minus the initial concentration, which was 0.1. Okay, we'll write that out, the sig figs, just save us time, divided by the change in time. And the change in time, so this would be the final time, which was 50 seconds, okay, minus our initial time, which is 0. Okay, and if you took those two guys there, you should end up with this average rate here. It should be going down by 1.9 times 10 to the minus fourth. Okay, and then you can do that for each one. And you can do it over the course of the whole thing, or individual 50 seconds. We could find the eventual, or the average rate of change for the whole thing by starting at 0 and going to 10,000 with 0. Okay, and we could find the average rate, and it would be slightly different. Now notice, you should notice here that the average rate between each of these times is actually getting smaller. Our reaction had 1.9 times 10 to the minus fourth molarity per second change here in the first 50 seconds, but in the next 50 seconds it was only at 1.7 e to the negative fourth, and then 1.6, and it's getting lower and lower as we go. All right. And so when we plot this reaction rate, okay, you can see that it doesn't make a straight line. It kind of flattens out. Our reaction is quicker when it first starts. Okay, and then it slows down as we go, and this is because our concentration is going down of our reaction, right? We just talked about in the last video has increasing the concentration would increase the concentration. If we decrease the concentration, then the reaction rate would also go down. Okay, and so when we're starting here, our reactant concentration was 0.1. Well, after 50 seconds, our reactant concentration was only at 0.090. All right, and so that's less, so because there's less reactants, there will be a slower reaction rate, and then we can keep going that way. And so as we keep going, we'll notice that this curve kind of flattens itself out. Okay, now the next, so we just did average reaction rate. Now we have instantaneous reaction rate. All right, so the instantaneous reaction rate is found by plotting the slope of the tangent line at a specific point. Okay, so right now they've done it at 600 seconds. Okay, so this spot right here is at 600 seconds, and then they drew a curve or a tangent line at 600 seconds. So it's just the straight line right across from here where it would touch this one point. Okay, and then if you find the slope of this line, you know what the instantaneous rate was at 600 seconds. All right, so that's the instantaneous rate. You just draw a tangent line and find the slope of that tangent line. Now, the initial rate is simply the instantaneous rate when you first start, or in this case when t equals 0. So an initial rate is the instantaneous rate. So it's found the exact same way. You pick your initial point, you draw your tangent line, and then you find the slope of that tangent line. All right. So this data here is from the previous example here. Okay. Just this data here just drawn out for us. Okay, so we could find the initial rate simply by taking these values. So we'd be at 0.10 and or 0.100 for the concentration is 0. All right, and then down here we would be at a concentration of 0.06, and then what is that, like 210 or so? Okay, and so we could go ahead and find the instantaneous rate here. Wouldn't be too hard. Okay. Wait. Yeah, we'll find the instantaneous rate here. So the instantaneous rate, okay, so we have, so our 2 points, so our initial, or our initial concentration, okay, was 0.1, right, 0.100, and then our final concentration was 0.060, 0.060, okay, it's probably more, we can't really tell, never mind, 0.060, I thought it was a point on the graph, but it's not. I just picked this point because it looked like it lined up nice with the spot here. And then time, our final time. Wait. Oh, I screwed this up, didn't I? It's final minus initial. Final minus initial. So 0.060 minus 0.100. And then our final time was 210 or so. And then our initial time was 0. Okay. So we can take our 0.06 minus our 0.1 divided by 210. Oops. Got to put it in your calculator, right, or it's not going to work. All right, and I got 1.90 times 10 to the minus fourth. 1.90 times 10 to the minus fourth. And it's negative because it's a reactant and it's going down in concentration. Notice that this is pretty dang close to what we got before. All right, for the average rate. Okay, average rate does a fairly good job if you do it over a fairly close time period. Instantaneous rate tells you the exact value, though it's a lot nicer. Okay. Now, relative rates is the ability of taking the reaction rate of one thing and being able to relate it to something else that's in there. All right. Now, this rate is dependent upon stoichiometry. Okay. So, in our original reaction here, this guy, our reactants and our products were in a 1-to-1 relationship, and we know that because their coefficients were 1. There's a 1 right here, and there's a 1 right here. Okay. And so they're in a 1-to-1 relationship between the two of them. Okay, and so as this goes down, this will get bigger equally, and that makes sense because all we're doing is we're taking this guy and replacing the chlorine with a alcohol group, an OH group. Okay, and so what happens is, specifically in this one, the rate is equal to this. We already established this, right? This was our reactant. It's going down over time. That's what the negative sign's for. And then at the same time, this one is growing equally, right? We've got our alcohol group here. And so as this drops, this one gets bigger, and it's a 1-to-1 relationship. Okay. In the next video, we'll talk about, well, what does that look like if it's not a 1-to-1 relationship? All right. But essentially, these values, the magnitude of these should be equal to one another. The only difference is the sign, whether it goes up or down. And the reactants go down in concentration, and reactants should go, or products should go up in concentration. All right, so let's do a couple practice problems here. From the data in figure 14.2, calculate the average rate at which A disappears over the time period from 20 to 40 seconds. So we got this beaker that's 1 mole of A, 0 moles of B. All right, and then we have 0.54 moles of A, 0.46, and 0.30 to 0.70. So we're doing a rate at which A disappears. Now notice these aren't in molarity and they don't give us a volume. So we're just going to do it in moles. So it'll be moles per second is the rate of change. Okay, so we're going to do a final. So it's from 20 to 40. So we're going to go here and here. This is 40 seconds. Okay, and so it'll be final molarity would be 0.30, and then we're going to subtract out the initial 0.54. Okay, so there's our final minus our initial for the moles of A, and then our time here would be final time, which is 40 seconds, minus the initial time, which would be 20 seconds. So we get 0.3 minus 0.54 divided by 20, and so we get negative 0.012. And what would our units be here? Well, it would be moles of A per second. Okay, not too bad. All right, let's see. Is there another one worth doing here? Let's do this one here. Use the data in figure 14.2 to calculate the average rate of disappearance of B over the time interval from 0 to 40. So now we're doing the same thing with B from 0 to 40. All right, so let's see. Well, let's do 0 to 40. So 0 to 40. Okay, so final B, so that's the 0.70 minus initial B, which is 0, over the final time, which is 40, minus the initial time, which is 0. Okay, and so it would be 0.7 minus, why am I doing that? It would be just 0.7 divided by 40. And so our rate would be 0.0175. All right, and really we could only do 2 sig figs here, so what did I say? 0.018. 8, and again it would be moles, but this time it's a B per second. All right, notice that it's positive because it's going up. All right, isn't that nice how that works out like that? All right. Oh, here we go. So now we're calculating instantaneous rate. We already did this one, actually, didn't we? From earlier, it says calculate the instantaneous rate of this at t equals 0. Let's see if they got the same answer we did. All right. Maybe. Yeah, 1.9 times 10 to the minus 4th molarity per second. That's exactly what we got before. All right, so let's do one more just to practice here. Okay, it says, which of the following could be the instantaneous rate of the reaction in figure 14.3, so that's the same one, at t equals 1,000 seconds. So we got to go to 1,000 seconds. All right, so what? All right, so now we got to kind of extrapolate what's going on here. So it's going to go like something like this, and 1,000 will be like right here. So okay, so really we're just going to be kind of guessing here. So we know, yeah, so it's going to be pretty low, right? It's going to be pretty flat. So let's see what our options here. This is just going to be a guess and check thing. 1.2 times 10 to the minus 4th. Well, it could really be more than one of these, couldn't it? That's really the answer, because really it has to be lower than... I don't really want to do this. Really, so what we'd have to do is we'd have to go through, and what I would do is I take this one here, find the instantaneous rate at 600 seconds, okay, because they've already got the tangent line for us made, so that'd be nice. All right, and then from here we can say, well, this is our baseline. We know it has to be lower than this, and then we could say, well, it's going to be more than one of these is probably what the answer is going to be. Let's do this one instead. Using figure 14.3, determine the instantaneous rate of disappearance of this at t equals 300. This will be better because 300 is on the dumb graph. All right, so 300 is right here. So this is our thing. All right, so we're going to draw our tangent line. All right, and this is where I fail miserably. All right, so here's our 2 points. So we've got 1 point right here, okay, at 300 seconds, and so that's like halfway in the middle, right? So that's nice. So so that's that one, and then we could choose any other point we want. So let's see, let's do this one here. All right, so that's at this point here, 0.60, and then it looks like it's about halfway, so it'll be at like 250 or so. Ish. All right, so final concentration. All right, so the final concentration, well, this would be the after one because we chose this point here. So the final concentration would be halfway between those, so it would be 0.055. All right, and then the initial concentration would be 0.060. Okay, and then final time would be the 300 seconds. Okay, and then the initial time here for our tangent would be I don't know, 250 or so. All right, so we can plug that into our calculator. Don't forget to use parentheses as appropriate, or you'll look like a fool. Divided by 50. All right, and we got negative 1.0 times 10 to the minus fourth, and it would be molarity per second. All right, so that would be the instantaneous rate. Not too bad. And that's it for this video here. We did some reaction rate problems, learned how to calculate average, instantaneous, and initial rates. All right, and then so next video we'll talk about, spoiler alert, what if your reaction is not in a one-to-one relationship? This is where life gets more exciting. All right, so do your practice problems. Let me know if you have any questions, and I'll see you on the flip side.